In this video, we're going to talk about the idea of a normal subgroup. That's a special type of subgroup. So to set the stage, I just want to observe again a phenomenon which we saw some videos prior to this. So I'm going to introduce a specific group. Let's let G equal S3. So that's the group of permutations on three elements. And let's let H be the subgroup generated just by the identity and the transposition 2, 3. We know that this is a subgroup because it has the identity, it has the inverse of this permutation because the inverse of this permutation is itself, and this set is closed under multiplication. Now I want to look at the left cosets and the right cosets of H and see whether they are the same or different. So we'll start over here. We'll leave the space over here for right cosets. Let's begin with just the coset H. The coset H just consists of the same elements as the subgroup H because the coset is the subgroup. That's also a right coset because I can think of this as being the identity times H, or I can think of this as H times the identity. By the way, as usual, epsilon is just the same thing as this permutation here, the one that does nothing. I don't know why I use different notation for it inside the set notation and outside. There's no real reason you have to do that. Okay, so that's one left coset, that's one right coset. By the way, I know that this group has 6 elements, and I know that this subgroup has 2 elements, so I should expect that the index of H and G, the number of cosets each way, should be 3. All right, so let's just see if we can find 3 cosets each way. All right, how about another left coset? Let's pick a different element to start out with. Let's try 1, 2, because I know that that's not in my subgroup. So that permutation times H, that coset is going to give me 1, 2, because I can always multiply this by the identity here. And then I also need to try multiplying 1, 2 by 2, 3, because that's an element of my subgroup. So 1, 2 times 2, 3. I'm going to say that that is equal to 1, 2, 3. And I'm going to leave you to check the work on that. All right. And then for a third coset, hopefully the last coset, I'm going to try an element that I know I don't have yet, which is 1, 3. Well, 1, 3 times the identity is just 1, 3. And then 1, 3 times this other element here, 2, 3. I believe that's going to give me 1, 3, 2. And again, I'm going to let you check the work on that. So again, I'm claiming that that is 1, 3 times 2, 3, the other element of my subgroup. Okay, so I think I have my 3 cosets there. And one thing you might remember, if we think of S3 as acting on the set 1, 2, 3, which is just about the most elegant action you can come up with for a permutation group, that is the weirdest 3. I don't think I've ever done that. I get absent-minded when I'm talking, I guess. The left cosets, each of them has something in common. Like each left coset has a special property with respect to the action of S3 on 1, 2, 3. If you look at the subgroup H itself, those are the two permutations that fix the number 1. So this sends 1 to itself. And then the second coset, these are the permutations, each of which sends 1 to 2. You'll notice this first one sends 1 to 2. And then the second one also sends 1 to 2. So each of these sends 1 to 2 under the group action. And then in the third coset, everything here sends 1 to 3. So the left cosets partition my permutations, and that's a tongue twister, in terms of what they send 1 to. Because I defined H to be the stabilizer, and I'm going to write this down. H is the stabilizer of the number 1. Okay, now let's look at how right cosets work out. Let's see if they work out the same or differently. Well, if I take a different coset over here, let's try H times 1, 2. Well, then I get 1, 2 because I take the identity times 1, 2. And then I need to do this permutation 2, 3 times 1, 2 with 2, 3 on the left this time. So if I do that, I think I'm going to get 1, 3, 2. Let's just check and make sure. So I get 2, 3, 1, 2. And if I look at what 1 is doing, this transposition sends 1 to 2. 2 gets passed over here, 2 gets sent to 3. So altogether, 1 is getting sent to 3. 3 doesn't do anything here, 3 gets sent to 2. So 3 is going to 2 here. And then finally, 2 goes to 1, 1 gets passed over here, 1 does nothing here. So I think that that's right. And already I see that that is not the same thing as my left coset for 1, 2. And if I calculate the other right coset, H1, 3, I will end up getting the other 2 elements. And I'll leave you to calculate and make sure that that's true. All right. Now, in terms of the group action, Here, when I look at the subgroup H times the identity, I still have all the permutations which send 1 to itself. But this time, what the elements of this coset have in common is a little bit different. This time, I have all of the permutations which send 2 to 1. That sends 2 to 1. This sends 2 to 1. So these all send 2 to 1. And then the other coset, all of these are permutations which send 3 to 1. So the right cosets of H partition, because H is a stabilizer of something, they partition S3 into sets, each of which sends the same thing to the number 1. So you might say that when H is a stabilizer, this is just a generalization, of some element X in a set being acted on, left cosets of H partition G according to the image of X. In other words, whether X goes to 1, 2, or 3. And right cosets of H partition G according to the preimage of X. In other words, what is getting sent to X, which I think is pretty cool. That's something that personally I didn't understand about group actions until I'd studied them a few times. And then when I started studying group actions on geometric spaces, it became imperative that I understand that very well. So I developed that understanding later in life, and I'm hoping to share a little bit of that with you. But now I haven't even mentioned what a normal subgroup is. So the reason I brought up this example in the first place was I just wanted you to observe, not so much about group actions in particular, I just wanted you to see that left cosets of a subgroup and right cosets of a subgroup, the same subgroup, they have the same size, but aside from that, they're not necessarily the same. And this is a key fact. Why it's a key fact is going to be revealed a little bit later. I have to admit that I'm going to give a definition here, and it's not going to be clear why we'd want this definition to be something that we study in group theory. That'll come along a little bit later. But for now, the main thing to observe is that left cosets and right cosets needn't have the same composition. They may partition the group differently. But now let's try a different example. Suppose I take H to be something else. And in fact, because I have H up there, I'm just going to use a different letter. I'm going to use the letter K. Let's let K be the subgroup of S3 that consists of all of the even permutations. Remember, even means it's expressible as a product of an even number of transpositions, which certainly is true of the identity because that's 0 transpositions, and each 3 cycle can be expressed as a product of 2 transpositions. This time, if I construct left cosets of K and right cosets of K, I claim that I can know without even doing any real work that these are going to be the same, but we'll see why in just a minute. So if I take the identity coset of K, that's just K. Same stuff I had before. Again, I don't know why I'm using epsilon for the identity over here and then parentheses 1 for the identity over there. They're the same permutation. I guess it's just habit. And then the right coset containing the identity, same thing. It's just the subgroup. It's just K. All right. So there does have to be some other coset because I've only listed out 3 permutations so far. But there's only going to be one other coset. I mean, here I have a subgroup of order 3 in a group S3 which has order 6. So there should only be 2 cosets. In other words, G, the index of K and G should just be 2 cosets each way. And because the epsilon times K or K times epsilon is just the subgroup, these have to be the same. Well, that means if I have one other coset and the other coset is disjoint from this one, it's going to have to contain everything else. So if I construct the coset 1, 2, K, I already know it has to have the other 3 permutations, 1, 2, 1, 3, 2, 3. And I didn't do that by multiplying these permutations by 1, 2 in any systematic way. I just did that because I knew these were the other 3 permutations in G. And those all have to be in this coset because the coset's got to have 3 elements. Same if I do this, k times 1, 2. I will again get 1, 2, 1, 3, and 2, 3. So this time, I have selected a subgroup K such that left cosets and right cosets of K are exactly the same. And when that happens, the subgroup that we use to create the cosets, this is called a normal subgroup. So to close the video, here's a formal definition of normal subgroup. All right, so the definition is, let G be a group. It could be finite, infinite, abelian, non-abelian, any group at all. Let G be a group, and let H be a subgroup of G. Then we say H is a normal subgroup of G. Let's include that in the underline there. A normal subgroup of G if the left coset AH is equal to the right coset HA for every A in the group. In other words, if the left cosets and the right cosets are exactly the same. I mean, saying that the left cosets and right cosets are the same is a perfectly fine way to put it colloquially, but we need eventually to have some way of proving that a subgroup is normal, and this is the way that we systematize that. We show that for every A and G, that the left coset AH equals the right coset HA, and if we can do that, we've proven that we have a normal subgroup. Now, I say that, but that's actually not how we're going to show most of the time that a subgroup is normal. We're going to have a more efficient way of doing it that'll be based on a theorem that we'll prove in the next video. I should also mention the word normal in mathematics doesn't mean what we often think it means in colloquial language. Like, normal makes it sound like most subgroups are normal, and then the ones that are not normal are bad. And it is true that the ones that are not normal are kind of bad. Like, they're unworkable in a way that normal subgroups are workable. However, normal subgroups are special. We shouldn't just randomly expect a subgroup to be normal. Sometimes it will be and sometimes it won't be. But normal subgroups, I wouldn't necessarily say that they make up most of the subgroups we encounter. We'll talk about that a little bit more in the following videos, but I just wanted to point that out, that being normal is a special condition. It's not something that we should expect by default.